Welcome to Physics 371 Online. This last topic in Chapter 3 is a really interesting one because unlike the other methods that we've talked about in this chapter, this is inherently an approximation method. And sometimes it's useful to have an approximate method for calculating the potential of a charge distribution, especially in cases where we're really interested in the behavior that it has in the limit of large distance away. Or if it's just a really complicated charge distribution and it's not easy to calculate the exact expression for the electric potential. So this multipole expansion method, as you might guess, being called an expansion, it's some sort of a series. And it's a series of terms where the idea is that each successive term gives a smaller and smaller contribution to the potential. So hopefully keeping just a few of those terms may give a good approximation. Here's the rationale. It's easy to write down the electric potential of a point charge at a distance r. And we know from our previous discussion that that potential is proportional to 1 over r. It's q over 4 pi epsilon naught r. And this is called a monopole, a single charge, a single pole. If we put two opposite point charges together and calculate the electric potential a distance r away from the center, it's easy to show, and this is done in the textbook, that the proportionality between the electric potential and distance is 1 over r squared. Makes sense that this kind of charge distribution has less of an influence as the distance gets larger than the single pole or the single charge does, and this is called a dipole. If we put two dipoles together, then we have what's called a quadrupole. And then if we measure the electric potential as a function of distance away from the center of the quadrupole, you might guess that the proportionality goes like 1 over r cubed, and so on and so forth. The next term would be putting two quadrupoles together to form an octupole, and that would be proportional, the potential would be proportional to 1 over r to the fourth. All right, so what this expansion, what this series of terms suggests is that maybe if we look at an arbitrary charge distribution, not just a collection of point charges, but some continuous distribution of charge of some irregular shape and a particular charge density, that maybe its overall potential can be written down as a sum of terms, each of which has a higher power of r in the denominator. And so that's the hope, and it turns out that we can actually do something like this. Now, can we do it rigorously? How do we go about doing that? First, we consider an arbitrary charge distribution divided into infinitesimal elements of charge dq. All right, so the charge distribution assume that we are given, it's rho of r, and then what we want to do is find the electric potential at a point p, a certain distance away from the charge distribution. So we set an origin and we define the three vectors that we've been using ever since chapter 2 to describe the geometry of this problem. First of all, the vector that locates the point where we're trying to find the potential, that is vector r. Then the vector that tells us the location of the charge element, that's vector r prime. And finally the third vector that tells us where the point in space is relative to the charge element, and that's script r. So you're familiar with this geometry. And you should also be familiar, or at least recognize, the expression for the electric potential as 1 over 4 pi epsilon 0 times the integral of rho d tau over script r. And the r prime and the tau prime indicate that the integral is over the primed coordinates. So in other words, we're integrating over the charge distribution and taking into account all of the r prime locations of the charge elements. So from the law of cosines, if we put the angle theta into this triangle as the angle between r and r prime, then we see that script r is r squared plus r prime squared minus 2r prime cos theta. And we can factor out an r squared term and rewrite this in the form shown right here. So that's going to be helpful in just a minute because we're going to use this expansion to find an expression for the 1 over r term which is in the integrand. So this allows us to write script r is regular printed r times the square root of 1 plus epsilon. You can see if I took the square root of both sides of this equation, I would have script r equals regular r times the square root of what's inside the brackets. Okay? And what's inside the brackets is 1 plus these two terms here. And I think you can see, right, the epsilon then is just the r prime over r quantity squared minus 2r times r prime over r cos theta. And that can also be expressed like this if we factor out the r prime over r. So what you see is that for a point in space far outside the distribution, all the values of r, the distance, are going to be greater than r prime. And that means these fractions that appear in the expression for epsilon will both be much less than 1. So epsilon itself will be a very small quantity. And the absolute value of epsilon will definitely be much, much less than 1. The double inequalities mean much. So because of that, because this epsilon term is much less than 1, the square root can be written approximately using the binomial expansion. Remember, the binomial expansion theorem tells us that 1 plus x to the nth power, where x is less than or equal to 1, is given in this form here as an infinite series. Each term contains a higher and higher power of the x that appears inside the parentheses, and you have a 1 factorial, 2 factorial, 3 factorial, and so on as you go out further and further. So we can take the expression here for script r and substitute in 1 plus epsilon overall to the 1/2 power. So when we take the reciprocal of both sides, we get 1 over script r is 1 over r times 1 plus epsilon to the minus 1/2 power. And we're doing 1 over script r because remember, that's what's inside the integrand, and when we're all done, we're going to substitute back into that. So here, 1 plus epsilon to the minus 1/2. If you just use the binomial expansion and then plug in each successively higher term, you'll get this expression here. The first term is 1, and then we have an epsilon squared, epsilon cubed. And remember, once again, that if epsilon is small compared to 1, every time you raise it to a higher power, you make it smaller and smaller. 1/10 squared is 1/100th, 1/10 cubed is 1/1000th, and so on. So these terms get smaller in a hurry if epsilon is small. All right, now let's take that expression that we just generated and go back and substitute in for epsilon. All right, what does that do? Epsilon is this kind of hairy looking expression. We'll take the far right hand side term, this one right here, and plug it in for epsilon, epsilon squared, epsilon cubed. And I'm just going to do that for you here, straightforward substitution. So we have 1 over script r is 1 over r times all these terms in the brackets, where we've got the 1, and then we've got the term which is the 1/2 epsilon, and then the 3/8 epsilon squared, and the 5/16, negative 5/16 epsilon cubed, and so on. And at this point, there's a little bit of algebra to be done because we need to expand the terms that are squared and cubed and do a little bit of rearranging. And so I will spare you the details of this, but all I do is expand those two terms, multiply through, and then rearrange. And what I'll notice is that my entire expansion can be written in a way that makes use of higher and higher powers of r prime over r. And so that fraction, that ratio, appears in the expression to higher and higher orders. So what you'll see is that there's going to be a first term which has r prime over r in it, and it's multiplied by cos theta. Then there's a term with r prime over r quantity squared. That, when we collect all of the terms, is multiplied by 3/2 cos squared theta minus 1/2. The next term has r prime over r cubed, and it's got a cosine cubed and a cosine term, and so on and so forth. So this infinite series contains a very interesting pattern. Do you see it? You see what the pattern is from previous exposure to problems of this type? Take a look. What you should notice is that each of the terms multiplying the r prime over r term is itself a Legendre polynomial. So the first term we'll call L equals 0. Well, that's P0. That's 1. That's kind of trivial. The second term has a cos theta in it. That's p sub 1. The third term, the 3/2 cos squared theta minus 1/2, that's p2. The next term has p3 in it. And so it seems almost miraculous, but these Legendre polynomials appear in lots of different cases when we're studying problems involving charge distributions and the electric potential. So this allows us to simplify this expression for 1 over script r as 1 over r times an infinite series that involves powers of r prime over r times the appropriate Legendre polynomial. That really condenses this whole expression. And what we now do is go back to the original expression for v, shown at the bottom, and substitute in for 1 over script r. And when we do that, we get this expression here. It's got the 1 over 4 pi epsilon 0 out in front, and it's got an infinite series of terms, each of which has some kind of an integral in them that has to be evaluated that depends on the charge density, and it depends on how the charge is distributed away from the origin. That's what the r prime indicates here. So let's take a closer look at this by writing out the first few terms on the next slide. But realize this is exactly what we wanted. We were hoping for some kind of expression for v that had successively higher powers of r in the denominator. So when we write the first few terms out, we see that that's exactly what we get. Here's the expression for v, and so we'll write out n equals 0. That'll have a 1 over r. Then we'll write n equals 1, which will have a 1 over r squared, and so on. So here's the first term, n equals 0. Note that it's got the 1 over r, and so it is what we call the monopole term, because it has the appropriate distance dependence for the electric potential of a single charge, the monopole. Then the dipole term is the next one because it has v proportional to 1 over r squared. The next one has the 1 over r cubed, that's the quadrupole term, and so on. So we could go further, but we'll stop here. And let's just notice that the monopole term simplifies in a special way. The other terms are more complicated to calculate, but we can do them. But note that the monopole term, if we integrate rho times d tau over the entire charge distribution, what are we doing? We're taking the charge per unit volume and integrating it over a volume. So what does it give us? It gives us the total charge of the distribution. So the monopole term is 1 over 4 pi epsilon 0 times the total charge over r. And that makes a lot of sense because that is exactly the way a point charge behaves. So it makes sense that the first term should be a term that tells us if this were just a point charge, that's what the potential would be. Since it's not a point charge, we have these higher order terms. The higher order terms reflect how the charge is distributed about the origin. If it were completely uniformly distributed about the origin in a spherical symmetry, then each of these terms, the higher order terms, would go to 0, and we would be left with just the first term. On the other hand, if your charge distribution has a distribution of positive and negative charge but overall is neutral, then the monopole term would go away, right? Because the total charge would be 0. So this captures a lot of very interesting physics. It gives us a prescription for calculating each term in this infinite sum if we know the charge density, if that's given to us. And again, as I have said, since each term will be successively smaller than the previous term, then to get a good approximation, especially at large distances away, all we really need to do is keep a few terms. So in class and later on in the textbook, we'll see some examples and we'll work some examples that show how to calculate the approximate electric potential of a distribution using the multipole expansion. I'll see you in class.